The strongest evidence we have today shows that deep beneath the icy crusts of Europa and Enceladus, moons orbiting Jupiter and Saturn, lies an entire ocean hidden in darkness. Scientists believe these oceans may host life, shaped by conditions similar to those that first sparked life on Earth, billions of years ago. We don't need to travel billions of kilometers into space. More than 2,000 meters beneath the Red Sea, right here on Earth, something exists that defies all logic. Gentle waves ripple across its surface, lapping against a shoreline of sediment, as if blown by an underwater wind. The surface of this lake pushes back when pressed, flexing and rebounding like a trampoline. Any creature that dares venture below the surface of this strange water never comes back. And yet, within this lethal darkness, a strange, primitive form of life exists. Utterly unlike anything we once believed possible on Earth. How can a lake exist at the bottom of the ocean? What kind of life could survive here? And what does it reveal about the very origins of life on Earth, and possibly beyond? The answer forces us to confront the possibility that we've misunderstood life from the very beginning. I'm James Carter, and you're watching True Earth. Join me as we descend into one of the most extreme environments on our planet and uncover what survives where nothing should. That discovery didn't begin with submersibles or cameras, but with a single measurement. March 1st, 1964. A short paper surfaces. English oceanographer Henry Charnock reports anomalous bottom water, nearly 2 kilometers below the Red Sea, far saltier than normal and shockingly warm. At depths where water typically hovers between 2 and 4 degrees Celsius, his instruments recorded 44 to 45 degrees in Discovery Deep. Beyond 60 degrees in Atlantis Too Deep, like finding a boiling kettle sitting at the bottom of a deep freezer. Stranger still, this separate mass of water appeared to be forming right on the seafloor. What he was seeing went against everything scientists thought they knew about the deep ocean. It wasn't until much later, as technology advanced, that scientists realized these brine pools weren't unique to the Red Sea, but also existed in the Gulf of Mexico and the Mediterranean. What do they have in common? To understand that, we need to take a closer look at one of these 3 places. Orca Basin in the Gulf of Mexico lies about 150 miles off the coast of Louisiana. It covers roughly 123 square kilometers, larger than the city of San Francisco. Beneath the surrounding seafloor lies a brine pool about 200 meters deep, a vast body of dark blue brine, surrounded by what looks eerily like a beach. This pool has existed for at least 7,900 years. How can a lake like this persist for so long without dissolving into the ocean around it? The answer begins with a very simple physical principle. When 2 liquids meet, the denser one sinks while the lighter one stays on top. You see it every time oil is poured into a glass of water. So what about brine pools compared to normal seawater? Ordinary seawater contains about 35 parts per 1,000 salt. Brine pools contain between 250 and 275 parts per 1,000, 7 to 8 times saltier. That's why these lakes stay at the bottom. Normally, when water with different salinity comes into contact, it quickly mixes. So what's stopping this brine lake from blending into the ocean around it? The answer comes down to two distinct natural processes working together. The first is called double diffusive convection. Imagine at the very bottom of the sea, you have water that is both warm and salty. Directly above it, you have water that is cooler and less salty. This means both salt and heat want to spread upwards. But here's the key thing. Heat spreads 100 times faster than salt. So what happens? Heat escapes first, leaving the brine colder. As it cools, the brine becomes denser, making it sink back down. This creates an invisible boundary, separating the brine from the surrounding seawater and keeping the two from mixing. But even with this boundary, salt is still crossing the line. The lake should eventually vanish, like a rock pool evaporating over time. And that's where the second process comes in. As brine slowly escapes into the water above, it is continuously replenished from below. So where is this warm, salty water coming from? And why does it appear in only a handful of places on Earth? In the past, the Red Sea, the Gulf of Mexico, and the Mediterranean were all enclosed seas, cut off from the open ocean. It happened during the Jurassic, about 160 million years ago, when the Gulf of Mexico was sealed off from the Atlantic Ocean by a narrow strip of land. More than 100 million years later, the Mediterranean suffered the same fate. By that point, the Red Sea had also been shut off from the Indian Ocean. Once cut off, with no new water flowing in, they slowly evaporated over millions of years, leaving behind massive salt deposits hundreds of meters thick. Imagine the entire Mediterranean filled, not with water, but solid salt. Over the following millions of years, that salt was buried by layers of sediment, pushed deeper and deeper into the earth. So when those dried up basins eventually rejoined the oceans and filled with seawater again, unique geological conditions were created. Above was a sea, below an enormous pile of ancient salt, separated by a layer of sediment. Over millions of years, layer after layer of sediment piles up, pressing down harder and harder on the salt below. But salt doesn't shatter like rock. When squeezed, it slowly oozes and creeps out of the way, like toothpaste being squeezed from a tube. As the salt moves, it bends and cracks the layers above. Through those cracks, seawater leaks down, dissolves the buried salt, and turns into ultra-concentrated brine deep underground. Warmed by heat from deep within the earth and squeezed by the layers of sediment above, this brine is forced upward. When it reaches the seafloor, it flows into natural depressions and settles. That is how an underwater salt lake is formed. And so far, there is no sign that this process has stopped. Observations made by NOAA at Orca Basin in 2018 made that clear. Here, brine waterfalls have been sustained for thousands of years by salt rising from deep underground, traveling upward through natural geological pipelines known as diapirs. In total, 3.62 billion tons of Luan salt have dissolved over the millennia, with around 500,000 tons added to the pool every year. This process has been ongoing for at least 7,900 years. A geological machine that has never truly stopped running. While the Orca Basin impresses us with its massive scale, one smaller feature within it reveals the true terror of these environments. Scientists call it the jacuzzi of despair, 4 to 5 times saltier than the surrounding seawater. This extreme salinity is immediately toxic to most marine life. It causes osmotic shock, violently pulling water from their cells. Salinity is only the beginning. Because the brine is so dense, it cannot mix with the oxygen-rich water above. Scientists have measured the dissolved oxygen here at just 0.0 milligrams per liter. For a fish, it's like swimming into water with no oxygen at all. Its gills keep moving, but there's simply nothing to extract. In the absence of oxygen, life here follows a completely different biological strategy. Methane becomes the foundation of everything that follows. Crabs, lobsters, and eels lie frozen in their final moments, some with claws still raised in defense. Others twisted into shapes that should not exist. Many of these bodies have been here for decades, mummified and embalmed by the extreme salinity. Scientists observed that fish and eels rarely approach the brine on this barren abyssal plain. When they do cross the boundary, most never return. Within seconds of contact, toxic shock from extreme salinity sends their bodies into violent convulsions, seizing and twisting as water is rapidly drawn from their cells. Nothing should survive here. Yet vast colonies of bright green tube worms stretch for hundreds of meters. Giant mussels, some over 100 years old, pack tightly around the shores. This mussel beach hosts shrimps, snails, squat lobsters, and jelly-like crabs. Larger predators, fish, octopuses, cutthroat eels, patrol the edges hunting for food, drawn to this oasis like animals to a watering hole on the African savanna. This entire complex ecosystem thrives at the boundary, the razor-thin edge where brine meets seawater, where the deadly and the life-giving converge. Life has found a way, not by conquering the toxic lake, but by mastering its margins. And one creature has mastered this edge better than any other. Hagfish. These slimy, eel-shaped scavengers lurk at the water's edge, waiting. The moment toxic shock takes hold of some unlucky prey, hagfish swoop in and snatch the body. Ancient creatures, even older than dinosaurs, often called living fossils, they resemble the very first vertebrates to appear on Earth hundreds of millions of years ago. What sets hagfish apart? While almost everything else dies within seconds, hagfish come and go as they please, diving in to catch their food, then swimming back out unharmed. The explanation lies in their biology. Hagfish are osmoconformers, one of the very few vertebrates with this ability. Their body fluids closely match the surrounding seawater. The salt levels inside their blood mirror the ocean outside. While the extreme salinity of the brine would eventually kill them, their unique physiology buys them time. Unlike other fish that seize up instantly, hagfish can resist the shock, diving in to steal food and swimming back out before it's too late. Genera like Myxine and Eptitretus have perfected this strategy over hundreds of millions of years. An elegant evolutionary solution to an impossible problem. But the real mystery is how this entire ecosystem sustains itself. Consider the mussels. Species like Bathymodiolus brooksii, Bathymodiolus childresi, and Bathymodiolus heckerae cluster densely along the toxic shoreline. Under a microscope, their shells reveal something extraordinary: methanotrophic bacteria, specialized microbes that feed on methane. They possess the PMOA gene, allowing them to oxidize methane. Some mussels host a single type of bacteria, while others host two, methane eaters and sulfur eaters working side by side. Among them, one species stands out. Bathymodiolus heckerae hosts 4 bacterial partners. These bacteria live deep inside the mussel's gills, supplying energy to their hosts. In return, mussels protect the bacteria from grazers and provide shelter to the shrimps, lobsters, and crabs living among them. Over time, these mussel beds grow dense and stable enough to begin shaping the brine pools themselves, keeping their edges from collapsing. Methane isn't the only fuel source here. Hydrogen sulfide, another toxic gas lethal to most surface life, saturates the brine. Thiotropic bacteria thrive on it, extracting energy from sulfur compounds, just as methane-eating bacteria do with carbon. In the Red Sea brine pools, this sulfur-rich chemistry supports entire microbial ecosystems, closely resembling the conditions scientists believe existed on early Earth. And for most of human history, scientists assumed all life ultimately depended on the sun. Plants capture sunlight through photosynthesis and form the base of every food chain. Even in the deep ocean, life survives on marine snow, organic debris drifting down from the surface. But brine pools break that rule. Here, life is powered not by sunlight, but by chemistry. Through chemosynthesis, bacteria turn methane and sulfur into food, fueling an entire ecosystem from the bottom up. The toxic soup that kills almost anything it touches actually sustains the ecosystem. Methane, deadly to most life, becomes the lifeblood here. Bacteria act as the primary producers, living inside mussels that anchor the food web. Shrimps, crabs, and worms feed on the mussels, while fish, eels, and octopuses prey on everything else. Such abundance in the middle of a vast, barren, abyssal plain operating independently of the sun's energy astounded the scientists who first documented it. These ancient life forms appeared to offer a window into how life might have first emerged. The discoveries continue. Recent studies in the Gulf of Aqaba revealed striking viral diversity in hypersaline deep sea environments, including giant viruses and entirely novel lineages previously unknown to science. In the Mediterranean, cat sharks use brine pools as nurseries, laying eggs along the toxic edges. Even more unsettling, scientists detected antibiotic resistance genes in Atlantis. Too deep and discovery deep, suggesting such resistance may be a natural phenomenon, not purely human-caused. These discoveries demonstrate that brine pools aren't just relics of the past. They are dynamic, evolving ecosystems, and their greatest secret may lie in what they reveal about the origins of life itself. But for over a century, scientists believed they knew where life began. 1871. Charles Darwin suggested life began in some warm little pond, a shallow tidal pool with heat, light, and electricity. This became the primordial soup theory. Life born in a rock pool, sparked by lightning. This idea persisted for almost a century, until the late 1970s, when the discovery of deep-sea chemosynthetic environments changed everything. Scientists discovered hydrothermal vents, enormous smoking chimneys at the bottom of the deep ocean, spewing torrents of superheated chemical soup from deep in the earth. Around these vents, they found an abundance of life, surviving not from the sun's energy, but from energy in that chemical soup, harvested by colonies of chemosynthetic bacteria. The discovery was groundbreaking, proving that life could exist completely independent of sunlight. Even today, more than 50 years later, hydrothermal vents are considered the most likely birthplace of life on Earth. Why? Because when alkaline fluids from deep inside the Earth mix with acidic ocean water, they create powerful natural energy gradients. In effect, a chemical battery. Minerals rich in iron and sulfur act as catalysts, helping hydrogen and carbon dioxide combine into simple organic molecules. A complete pathway from non-life to life. Now there's another contender. Before brine pools were discovered, it seemed impossible that life could survive in such extreme salinity. But in recent years, the discovery of rich microbial and complex life there has expanded where we think life can exist. Scientists believe Earth's primordial oceans, between 3.5 and 4 billion years ago, were low in oxygen, rich in methane, and far saltier than today. What else fits that description? A brine pool. The resemblance is remarkable. It suggests that brine pool environments may closely mirror the conditions of Earth's ancient oceans at the very moment life began. While brine pools mirror many conditions of early Earth, they still lack a clear chemical pathway for how life could first emerge. Hydrothermal vents offer such a mechanism, with proton gradients driving carbon fixation. So brine pools may not tell the full story, but they expand our understanding of where life can exist and suggest just how resilient and creative life can be. Could environments like brine pools exist elsewhere in the solar system? And if they do, could they harbor life? Two of the most likely contenders are Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. In 2009, NASA's Cassini spacecraft detected ice grains rich in sodium salts erupting from geysers on Enceladus. Dissolved salts, the unmistakable signature of a salty liquid ocean beneath the ice. These oceans may be as salty as Earth's early seas, where briny oases of life may be hidden. We'll learn more in April 2030, when NASA's Clipper spacecraft arrives at Europa after a journey of 2.9 billion kilometers. Whether life exists in those distant oceans remains an unanswered mystery. But one thing is certain: brine pools have shown us that life does not require sunlight or oxygen to exist. In the darkness, miles beneath the waves, there are still mysteries left to solve. From unexpected viral diversity in the Gulf of Aqaba, to shark nurseries hidden deep on the seafloor, to ancient life forms that predate the dinosaurs. Who knows what secrets might still be lurking below the surface, just waiting to be found. Mysteries that might hold the key to understanding not just where we came from, but where else life might exist in the universe.